Welcome back to Past Paper Walkthrough. Today we're doing the AQA GCSE Chemistry Paper 1. Oops, that's my pen. So we're doing the higher tier, the second part of it. So we have spent, I think, 50 odd minutes on the first half of the paper, which is not ideal, but I've kind of wasted a lot of time trying to explain things. So let's see how it goes. And also, I think for this particular question where I plotted a bar chart, I don't think I showed it that well in terms of, it's just because paper size is a bit big and my screen is not big enough to encapsulate everything. So yeah, I'm sorry if it's not clear. Right, so we are back with question 6. And a student investigated electrolysis of different substances, and we have a DC supply system ready. So you've got graphite electrode, zinc chloride solid, and crucible. Why electrolysis would not take place in the apparatus? So electrolysis requires a flow of ions, and solid zinc chloride is not, well, there aren't any flowable, free-flowing charge to carry the current, which to get the 2 marks, basically just say that zinc chloride is not, I assume it's zinc 2 ion, but in reality you would just write out zinc chloride in English, then they can't really penalize you for making a wrong assumption. But from what I know, zinc does exist with 2+ ion charge typically, and it's not molten or dissolved. So no free flowing charges or ions can carry the current. So basically that's all you're asked to say. So 2 marks, 1 to say that you need free-flowing charges, and 1 to say what this, because you to explain that zinc chloride in solid is not conductive. Second part, why graphite conducts electricity. So this is more to do with the bonding in covalent structures. So again, basically bookwork, remember this method of answering graphite questions. It's 3 marks really. So it forms it forms 3 bonds for each carbon atom, which means, so there is 1 electron that can be delocalized. So it's the delocalization of the electrons that can carry the charge, carry the current. So what really you need to say that the electron can flow through the entire graphite structure. So the delocalized electron can flow through the entire structure, so it conducts electricity. Oops. It would be helpful if I learned how to spell electricity, but oh well. Yes, so for the 3 marks, it's to state a delocalized electron for each atom of carbon, and to say it can flow through the entire structure. So it's the structure that matters, not the layer of graphite. So instead of the electron going in this direction through the graphite layers, it's trying to get at the electron flowing through the across layers. So that's just how they want you to answer things. It's just, again, phrasing unnecessary kind of fuss that examiners enjoy. Right, so the student investigated how volume of gases produced changes with time in the electrolysis in sodium chloride solution. So if you do remember from your lessons, sodium chloride solution, which is salt, water, or brine, will make hydrogen and chlorine, and it's also quite kindly given to you right here. And the 6.3 is the student made an error in selecting apparatus. How should the apparatus be changed? Right, so apparatus, you're looking at the glassware and you're looking at everything else. You've got a stop clock, looks alright. You've got a DC power supply, that's what you want. You don't want AC for your electrolysis. You've got a kind of bung in a glass kind of funnel container, which it could be a leak hazard, but for now, so for now, just note that down on the side just to keep it in your mind. Then you proceed to look at the solution itself, sodium chloride, which is what you want to react. That's fine. Graphite electrodes, they do conduct electricity. That's fine. Now for the last apparatus, which is what the question is basically getting at, there's a reason why I started from the bottom, because I know the correct answer is up top. But so test tubes for measuring volumes of gas, not the best, because you don't know what the volume is. You can calculate it to a good approximation using geometry or 3D geometry, but it's not adequate in terms of your experimental protocol. So what you really want to change the test tube for is that you want to use a measuring cylinder instead. Because if you use a measuring cylinder, it's graduated. You know the amounts that you've collected, and you can just calculate the rates a lot easier. Yeah, so that's a volume of gas is the measurement that we're taking. Right, we've got that. One reason for your answer, so 1 mark for saying it's the measuring cylinder for test tube, and the second mark being that it helps you measure the volume. So that's that part. another student used the correct apparatus. Good for that student. This student measured the volume of gas collected every minute for 20 minutes, and this is the result. So yeah, I probably can't fit this in my video in total, but I'll try. So the question being, describe the trend shown in the results and use value from figure 8. Figure 8 being this graph, and I think I'm gonna try to fit it in, but it's probably gonna cut off just about here. Right, so the trend, so if you look at the hydrogen produced, it's from 0 to a maximum value of 9 at 20 minutes. And for chlorine, it's also starting from 0, except for the fact that it takes a while to build up. And by 20 minutes, you're gonna get to a value of 6.6 cm cubed. So basically what you want to say in terms of the trend is hydrogen evolved is linear, whereas for the chlorine you have a build-up period before it gets linear. So so between 8 minutes and 0 minutes, the chlorine gas is slow to go, but after 8 minutes it gets linear in terms of the rate. So first mark for linear hydrogen overall, second mark is between 0 and 8 minutes for chlorine, and third mark is between 8 and 20 for chlorine. Now you've got the next question is the number of moles is the same on each electrodes. No gas escaped from the apparatus, and suggest a reason for the difference in volume for each gas collected. So in terms of the total volume of gas collected, we can tell that chlorine is definitely less than hydrogen. Now we apply our knowledge of molecular gas molecules. Hydrogen is not a halogen, but it is a dimer in gaseous form, so H2 as the gas. Chlorine as well as Cl2 as a gas, which means that in terms of number of mole, they should have the same number of moles, which means that they should have the same volume due to ideal gas laws. But there is a distinct difference in gas volume, but it does seem a bit difficult in terms of what you should be answering here. But I'm not sure if they took this off the spec or not, but I'm pretty sure that, oh wait, no, it's A-level knowledge actually. So chlorine as a gas does dissolve in water. So that is that's where the chlorine went. When chlorine dissolves in water, it goes into something called a chlorate, and under UV exposure that would become, I think it's HCl as a byproduct. But I need to check that. But for the purpose of this for the purpose of this exam question, it's one of those that is worth 1 mark, and it's kind of extended knowledge where chances are you're not going to be able to get it unless you really do read up yourself about things. So yes, so the solution for this would just be chlorine gas reacts with water or chlorine gas dissolve in water. So take this question with a grain of salt, because I would myself. 6.6, calculate the amount in moles of chlorine collected after 20 minutes using figure 8. Wait, that's after figure 8, right? Yes. So, right. After 8 minutes, you have essentially just a triangle, and we know exactly how much volume we have from marking out where it starts. So from crudely, it's this is 1 cm cube up to 6.6, which means that we have 5.6 cm cubed of gas. So 5.6 cm cube of gas, and now we have standard room temperature and pressure, which means that we're using the ideal gas law, and we convert the that's quite nice of them. So it states that 1 mole is this volume, and so in order to get this volume, it's a bit of algebra. So we know that we have X number of moles of gas, and if we divide that by 1 mole, we get 5.6 over 24.0. 5.6 is in centimeters cubed, which means that we times 10 to the minus 3. So that's how you calculate the ratio. Essentially, it's just a ratio calculation, which is quite nice. And that one should give you something along the lines of 2.75 times 10 to the minus 4 moles. So that's the answer to this part 6. So make sure you give your answer in standard form, so it's in times 10 to the power rather than 0.000275. Question 7, group 7 elements which are halogens, so write that down. Just to remind yourself, chlorine is more reactive than iodine. Name the product formed when chlorine solution react with potassium iodide. So chlorine solution is Cl2 in aqueous solution. Doesn't really matter in terms of the equation. So we've got Cl2 and potassium iodide. We know that iodine is a halogen, it's a 1 minus ion, whereas potassium is group 1, which is a 1 plus ion, so it's a 1-to-1 ratio. And when they do react, they need to do an ion exchange, and so the chlorine would become chloride, so you have 2 chlorides, whereas on this side you're gonna have to balance it with 2, which gives you 2 loads of KCl plus I iodine too. So the in terms of the question, it's named the product form, so you can just write KCl and I2. Alternatively, you can write potassium chloride in English and iodine in English. That's also accepted. The equation itself doesn't matter, so it's just kind of a way for me to explain what's going on, really. So explain why chlorine is more reactive than iodine. So halogens forms ions by gaining electrons, which we already know because most halogens most halogens bond in ionic form, and even if you bond covalently, you still need to attract an extra electron. And halogens form ions by gaining electrons, and the atomic radius of chlorine is smaller than iodine. So that's the main difference in terms of the halogen series, is that iodine is much, much bigger. And so the nucleus to electron attraction is stronger in chlorine, so it's gain electrons more easily. So that's basically just 3 marks. You have smaller atomic radius, stronger attraction, and hence gain electron more easily. So these are the 3 main marks that you're getting. 7.3, chlorine reacts with hydrogen to form hydrogen chloride, HCl. Explain why hydrogen chloride is a gas at room temperature in terms of structure and bonding. So we know that HCl is covalent and a simple molecule, so it doesn't form any big structure, which in theory the covalent bond is very strong, but it is not the covalent bond that defines its state. It's the intermolecular force that is holding the thing together. In this particular situation, it's the permanent dipole interaction between the hydrogen chlorides. So you have weak intermolecular forces hold the molecules together. And so the last thing to say is it is easy to overcome the intermolecular forces to cause a state change. So that's basically the 3 marks. You've got simple covalent structure, and you need to talk about the weak intermolecular forces, And finally, it is very easy to overcome such weak force to change its states. So that's that part done. Okay, question 7.4 is a reaction using bond energy. So that is a very standard type of question that you can get. So you've got bond energies given to you and you have overall energy change given to you. So there are multiple ways of doing this question, and let's just first consider how much energy we're getting in either side of the equation. So we know that the energy input to the system is equal to the energy output to the system, which means that the amount of energy we put into breaking bonds equal to the energy that comes out from forming the bonds. And of course you have to consider the overall energy. So on the left, we have a methane, which is 4CH4, which is 4 lots of 412, and a BR-BR bond, which is 1 lot of 193. So that's simple. We've got now on the right-hand side, 3 lots of 412, 1 lot of X, which is CBr, and finally we have 1 lot of 366 in the HBr bond. So if we put in the numbers, which is, so we want to sum the left hand side and sum the right hand side, which would give me at the bottom 1841 on the left, and let's see, 412 plus 366 is 1602 plus X. So we've got these two, and we need to realize that on the left we're breaking, so it's negative in terms of energy change, and on the right we're forming bonds, which is positive in energy. And so this 1841 is actually negative. Now we're going to consider the overall energy change, which in this case, because we're considering breaking this as a negative change in input, that would mean that the overall energy change is negative. So you just add minus 51 on the left. And that all added together must equal to 0. Just because of the conservation of energy. So if I just restate what I've done, is that I have used energy. That's an interesting mechanic of this notepad that I have no idea what I've done, but oh well. So, use energy to break bonds. Then here we have the change of energy. And finally, here we have the form release energy. So all of those three would sum to 0. And if you do it using your calculator, which is 1602 minus 51 minus 1841 is minus 290 equals to, whoops, it's x minus 290 equals to 0. That's just a copy mistake which happens, and hence x is 290 kilojoules per mole. Bear in mind that bond energy is always positive. Now question 8, we have titanium as a transition metal, suggest one hazard associated with stage 1. So there are many hazards. So your number 1 using CO2 gas, which is toxic. Number 2, you're evolving in carbon monoxide gas, which is also toxic. So either one would do. I'd say Cl2 is toxic. That's the biggest hazard that I can think of, because I guess chlorine is more toxic than carbon monoxide in a way. Now 8.2, water must be kept away from the reaction in stage 2. Stage 2 is titanium tetrachloride plus 4 sodium into titanium and 4 sodium chloride. Why water must be kept away from the reaction of stage 2? Because it even told you it's a sodium. So why is it hazardous? Well, we know that sodium is a group 1, not halogen, but alkaline metal, which reacts with water vigorously to form sodium hydroxide and hydrogen gas. So there are many ways that you can answer it. You can say it is highly exothermic. You can say that it forms a very, very corrosive base, or you can just say it makes hydrogen gas. So that's the easiest one that I can write down without explaining too much. 8.3 suggests why the reaction in stage 2 is carried out in the atmosphere of argon and not in air. So stage 2 again, it's titanium tetrachloride and 4 sodium. Again, something to do with sodium. In terms of the question, it's extracting titanium, so I guess we want to preserve the titanium as well. So air contains oxygen and water. It's just how our air atmosphere is made, and hence it reacts with sodium and or titanium. I don't know why I wrote sodium in English, but oh well. It reacts with sodium and or titanium to form oxides or hydroxides, and that is not ideal. And I think if you just write argon is inert. So comparing the argon and air, we know that argon doesn't react with anything most of the time, and air contains oxygen and water, which will react with our reagent and potentially contaminate them, so that is a bad thing. So 2 points in terms of sodium reacts with the atmosphere is 1 mark, and argon is inert or doesn't react is another. Now we have 8.4, titanium chloride is a liquid at room temperature. So just why you wouldn't expect titanium chloride to be a liquid. So what you expect titanium chloride to be is, well, a solid, because it's ionic structure. It's a metal bonded with a halogen. So expected giant ionic structure. And so STP, standard room temperature, and well, standard state and temperature and pressure would be solid, as we have seen a lot of ionic substances being solid. And that would be due to strong, I don't know what that tongue thing is, but so due to strong electrostatic forces. And so again, this is just trying to get you to talk about strong electrostatic force for ionic bond. So one mark ionic, giant ionic, one to say it's solid, and one to talk about the electrostatic force. Stage 2, sodium displaces titanium for titanium chloride. Sodium atoms are oxidized to sodium ions. So what is an oxidation? Oxidation is loss of electrons. And you probably, if you haven't heard of this before, oil rig is the way that we remember oxidation and reduction. Oxidation uses O, and so this is a loss. And rig is reduction, and so it is a gain. So this is just a way to remember it. Has nothing to do with crude oil, but oh well. Now complete the half equation for the oxidation reaction. Half equation involves electrons, so I'm going to put one electron in right there. I know that sodium is a group 1 alkaline metal, which means that if it loses one electron, it's going to be a sodium 1 plus. So nothing too difficult here. Now 8.7 in stage 2, 40 kilogram of TiCl4 was added to 20 kilogram of Na. The equation is, oh, it's given, nice. So we have the AR and explain why titanium chloride is the limiting reactant, and you must show your working. So basically telling you to work out the number of moles of each thing. So let's work out the number of mole of sodium, which is, wait, how many grams is sodium? 20. So I've got 20 times 1000 grams. If you're working in MR or AR, you work in grams. And sodium is 23, and that would be the number of moles. And that is 870 moles. And now we have to consider titanium chloride. So the MR of titanium chloride is 4 lots of 35.5 at 48, which is 190. And with that insight, we are using 40 kilogram of titanium chloride. So 40 kilogram divided by 190, that would give us 211 moles. So round to 3SF, or maybe you, right. Now you've got 211 versus 870. Which one is in excess? Which one is limiting? Quite obvious, but do write down therefore. Titanium chloride is in deficit or is a limiting reagent. For stage 2 reaction, percentage yield 92.3, theoretical maximum mass produces 13.5. So that's wait, they actually seriously tell you to calculate this. Okay, what this is like, this is pre-GCSE math multiplication, isn't it? So you basically have 13.5 times 92.3 times 100, which, oh wait, actually divide by 100 because we're taking away the percentage. So, right, calculator, 13.5 times 0.923 gives you 12.5 kilograms. I actually can't believe they actually put this in. And okay, I'm so disappointed in the exam board actually. Right, question 9, this is the final question of the paper. This question is about acid and alkalis, so acid-base reactions. Dilute hydrochloric acid is strong acid. So basically this is explaining what dilute and strong means. So strong is any acid that can ionize completely. So any inorganic, well, most inorganic acids are strong acids, like sulfuric acid, nitric acid, hydrochloric acid, things like that. Then you've got dilute, which is low concentration. So that's well, probably better to say dilute or low concentration of proton or H plus ions, but I think that might be A level, I can't quite remember. So now 9.2, we have a concentration given in acid. Okay, this is, again, the exam board change their spec every year, and there are things that I think you should know and there are things that I think you shouldn't know, but I don't think you should know that pH can be measured by minus log base 10 of the hydrogen ion concentration. I don't think this equation is in spec, but it might be nowadays. Do let me know. But basically, if you run this concentration of hydrogen ion, you're going to get 5.0. And that's just how it is. And yeah, it's also quite obvious to find that it's actually the negative of the power of 10. So the negative of power of 10 of 1 times 10 to the minus 5 is just plus 5. So you have a pH of 5. Yeah, I'm gonna skip that now. A student titrated 25 cm cube of dilute sulfuric acid with 0.105 moles per decimeter cube sodium hydroxide solution. Number one thing to check is you've got sulfuric acid. This is 2 equivalents in acid. Sodium hydroxide is 1 equivalent of base. Now you've got the reaction equation here, and we know we have the volume of the titration and use concordant results, and it's given that concordancy is 0.1 cm cubed. So this is definitely not concordant. These two are far apart, and so these two are not used. Now you have these two are 0.05 apart, which is half of the concordancy limit. And 4 and 5 are just exactly the same. So we're using these three. Right. And hence we get that the volume of this is 22.13 cm cubed for the titration. And in terms of the number of moles of base that we have, sodium hydroxide uses this concentration per decimeter cubed, and so we convert the actual cm cube volume into dm cube, which is 0.02213 dm cubed. This multiplied by conc of 0.105. Oops. Moles per dm cubed, and so that would give me 0.2213 times 0.105 is 0.00232. That's in moles. And we know that one lot of base can deal with, well, you need 2 moles of base to equal 1 mole of acid. And so the number of mole of acid is actually half 116 mole of acid. So you've got half the amount of acid molecules. And finally, we know that the total volume for the acid is 25 cm cubed, which means that you divide that by 25 times 10 to the minus 3 dm cubed, 0.0465 in 3D decimals, or 3dp rather. dp? Significant figures, SF, yes, 3 SF, in moles per decimeter cubed. And yes, so this is the concentration. Yeah, I thought I made a mistake because I forgot to divide by 2 right here on my calculator, which is kind of funny, because I thought I did, but Oh well, that's not important. So now we have found the concentration of sulfuric acid in moles per decimeter cubed. And we move on to question 9.4. Explain why the student should use a pipette to measure dilute sulfuric acid and a burette to measure sodium hydroxide. So pipette gives an accurate volume, whereas burette gives a variable volume. So the pipette is important because you want your test liquid of unknown concentration to have the same number of mole every time, which means that you need the same volume every time. The sodium hydroxide solution, however, is a given concentration, which means that you want to change its volume in order to get more information out of the system. So basically it's just a question to talk about the difference between burette and pipette. And the last question, 9.5, calculate the mass of sodium hydroxide in 30 cm cubed of that solution. So 30 cm cubed, again we're working back to the mole, which is 30 times 10 to the minus 3, that's decimeter cubed, multiplied by the concentration, mole dm cubed, which gives me let's see, it's 3.15 times 10 to minus 3 moles, and I know that the MR is 40, kind of them giving you the MR, which I know that if I multiply MR with the number of moles, you get the mass, which is just 0.126 grams. So yeah, this is it for this paper. It's not the hardest paper, but some of these longer questions do take a bit of thought, and I think the more challenging ones would be to be able to use bond strength or bond energy to calculate the unknown bond enthalpy, which again it's still within reach. This is a higher paper, it's meant to be challenging, but yeah, that's it for this video. I hope you've learned something. If you have, do let me know in the comment section below.